So this video is going to have a look at the extraction of iron. So this follows on really from the chemistry of displacement reactions and then the chemistry of redox, which you've already studied in this topic. If you don't understand displacement reactions and you don't understand redox, you really need to go and have a look at those. Anyway, we're going to look at the case study then, which involves the extraction of iron and the extraction of iron from its ore, okay? And this is done in the blast furnace. We'll have a look at the blast furnace in a bit more detail in the next couple of slides. The ore that you have to know about is hematite. You have to be able to spell it correctly. It is a technical word, so make sure you can spell it properly. And the compound, the iron containing compound within that is iron 3 oxide, which you need to know the name of and the formula of course. This is what it looks like, and you can see probably the reddish tinge of that hematite. That's the presence of iron 3 ions, which are a reddish colour. Now, into this blast furnace we add not just hematite, which is the iron containing compound, but you also have to know that you add coke, which is essentially a slightly impure form of carbon, which is made from heating coal, and when you heat coal in the absence of oxygen, it doesn't burn. But what it does do is you drive off all those sort of volatile chemicals that are in the coal, and you leave carbon behind. Not totally pure carbon, but fairly pure carbon. The other things that go into this blast furnace along with the hematite are limestone, and essentially the chemical within the limestone that we're after is calcium carbonate. We'll have a look at that a little bit later on as to what the importance of calcium carbonate is. And then we're also putting in hot air, and what we're after from the hot air is hot oxygen. Okay. So we would never use pure oxygen. The temperatures would be too uncontrollable and you have to pay for pure oxygen. Air is, on the other hand, free. Okay, so those three substances that go in there are all known as the charge. Okay, so you've got the iron oxide, the iron 3 oxide, the coke and the limestone, and the hot air comes in from the bottom of the blast furnace. So this is a sort of a diagram of a blast furnace. You can see at the top there we've got the charge going in, we've got the iron ore, the coke and the limestone. We have an exhaust for excess hot gases, and then basically what happens in this process is that a variety of exothermic chemical reactions happen as we go down. You can see the temperature rises from 400 degrees right up to about roughly 2000 degrees Celsius, where the iron at that point, which is made, can be topped off as molten iron from a tap hole at the bottom of the blast furnace. The waste material is a compound called slag, called calcium silicate. Actually, the compound, the chemical name, mostly, not all of that, but as far as you're concerned, calcium silicate is slag. That's also tapped off from a different tap hole, okay? So let's have a look. We need to know how the reducing agent for this process is made. We need to know the chemical reactions that happen at each stage of the process. We need to be able to categorize those chemical reactions in terms of combustion, exothermic, oxidation, reduction, redox, neutralization, acid-base, thermal decomposition. So this can come up as a really significant question worth quite a lot of marks. So make sure that you know it really well, and make sure that you know the equations well, and you're able to categorize those equations. So we're going to look at the reactions that happen in the various stages of the blast furnace now. Production of the reducing agent, as I said, the reduction of the iron 3 oxide and removal of impurities to make sure that our iron is actually useful. So stage 1, which happens initially in the blast furnace, is where the coke, which is remembered as carbon, burns in oxygen to form carbon dioxide. Okay. Now that's a really exothermic reaction, gives off lots and lots of heat. So it's a combustion reaction, it's an exothermic reaction, it's an oxidation reaction, but it's a carbon's gaining oxygen. So you have a whole variety of reactions going on in there that you have to be familiar with, as well as knowing the word and balance symbol equation. Now within the blast furnace, that carbon dioxide is made there reacts even further because of the heat inside the blast furnace with more carbon, and it gives you a compound called carbon monoxide. So you can see there that is actually a redox reaction, because the carbon is starting off with 2 oxygens on the left hand side Now it only has one, so it's lost some oxygen reduction, and the carbon on the left hand side has no oxygens on it there. Now it has one, so it has gained some oxygen. So you've got oxidation and reduction based on gain and loss of oxygen here. Okay. Now the carbon is in this instance gaining the oxygen and is therefore oxidized. So anything that's being oxidized is the reducing agent. Okay. So the carbon here has gained oxygen, so in this instance it's the reducing agent. The carbon dioxide here has lost oxygen, it's reduced, so it's what we call the oxidizing agent in this particular reaction. The whole point of this reaction is to make carbon monoxide, and that carbon monoxide is going to be the reducing agent, which actually converts our iron 3 oxide into our pure molten iron. And this is what happens in the next stage of the blast furnace. So you can see now the iron oxide, which has come from the hematite, reacts further with that carbon monoxide to give us finally our iron and our carbon dioxide. Now it's so hot in here that this iron is formed as a molten form and can be tapped off quite easily from the bottom of the blast furnace. That is an equation which students have difficulty balancing, so make sure you are either good at balancing equations, or alternatively you need to learn that equation off. It's not that difficult to learn off. The numbers are 1, 3, 2, 3. It's okay, but either way, make sure that you know it, because it will come up if there's a question on the blast furnace. And that molten iron, as I say, is tapped off at the bottom of the blast furnace. Again, this is a redox reaction. You can see that the iron oxide over here has lost its oxygen, and that the carbon monoxide, which had one oxygen on it here, now the carbon has 2 oxygens on it. So the iron oxide is being reduced, losing its oxygen, and the carbon monoxide is being oxidized, gaining oxygen. So therefore it's a reduction reaction. Now when you make iron in this way, you're going to have some impurities in it, because if you remember earlier, we put some hematite in there, and hematite is a rock, and within a rock are a whole variety of impurities, and those impurities have to be removed, because if they aren't, the iron that's made in the blast furnace is essentially useless. It becomes very brittle, basically. Now you only need to know how one of the impurities is removed, and we're going to look at that now. So this is where our limestone or calcium carbonate comes into play. And if you think about earlier, we haven't talked about the calcium carbonate apart from saying that it was actually put into the charge in the top of the blast furnace at the start. So the first thing that happens is the calcium carbonate gets thermally decomposed. The heat in the blast furnace is enough to break it down into, in this case, calcium oxide and carbon dioxide. So this is a thermal decomposition reaction, which is an endothermic reaction because it's taking heat in. Now the key thing about this is that this calcium oxide that is made here has basic properties. If you remember back to your acid base topic that we did, we said that metal oxides or bases have basic properties. You can see that in the blue box at the bottom. Now, when we put hematite into the blast furnace, as I said earlier, hematite contains a certain amount of iron 3 oxide, but it's not all iron 3 oxide. It contains a whole load of other things like clays and sands and silts, which are impurities, and they ruin the properties of iron. One of the biggest impurities is sand, which is essentially silicon dioxide, SiO2. If you notice silicon dioxide, that is a non-metal oxide, so therefore this has acidic properties. So we have silicon dioxide with acidic properties, we have calcium oxide with our basic properties. We react those together to form a compound called calcium silicate, which is essentially a salt, and that's a neutralization reaction where we have acid reacting with base. Now this impurity now pulls the silicon dioxide out of the molten iron, which makes it much more pure and much more useful. This calcium silicate that's formed is commonly called slag. It floats on top of the iron. It's less dense than the molten iron, floats on top of it, and it can be tapped off through that tap hole that we looked at earlier when we looked at the diagram. And it's used for a variety of things, building roads, making blocks. Okay, so it's not complete waste. It may be a byproduct, but it's not waste. Okay, so that pretty much covers all of the chemistry and all of the reactions in the blast furnace that you need to know in the manufacture of iron. We'll look further at this topic about rust and how to prevent rust and what rust is and the chemical process that happens in order to make rust. Okay, so hopefully that helps, guys.